In this video, we're going to look at solving log equations. So in the last video, we used the one-to-one property of exponents and the definition of a log in order to solve exponential equations. So now we're going to look at the one-to-one property of logs, and again, that same definition of a log in order to solve log equations. So first of all, let's do the one-to-one property. So the one-to-one property of logs says if the log base b of x is equal to the log base b of y, so we have two logs with the same base on both sides of the equation, then the arguments of the logs have to be equal as well. So x has to be equal to y. Okay. Now keep in mind though, from when we studied logs to begin with, the domain of a log has to be positive. So keep in mind here that x has to be greater than 0 and y has to be greater than 0. Okay, so they have to be positive. This is going to give us an extra step in solving these log equations that we didn't have in the exponentials, of checking our answers to make sure that they fall within the domain of the function. All right, let's go ahead and look at some examples. Again, solve each equation. Okay. So let's start with the log of x plus 7 minus the log of 3 is equal to the log of 7x plus 1. All right, we're going to use the one-to-one property in order to solve this. All right, now you may be looking at this and saying, wait, that doesn't quite match our one-to-one property. The one-to-one property has one log on the left and one log on the right. We have two logs on the left and one log on the right. So in order to be able to use the one-to-one property of logs, you might first have to use your product rule, quotient rule, or power rule in order to condense the logs and then use that one-to-one property. So in this case, if we look at the left-hand side, because these two terms are being subtracted, we can use our quotient rule in order to condense these. So the left-hand side would become the log of x plus 7 divided by 3. And the right-hand side just stays the same. All right, well, once we condense that left-hand side, now we can use our one-to-one property because we have one log on the left and one log on the right, both with the same base. So the one-to-one property basically allows us to drop the logs and set the arguments equal. So we would have x plus 7 all over 3 is equal to 7x plus 1. All right, now we just have a linear equation to solve. So if we want to solve for x, we've got to deal with this 3 first. So we can multiply both sides of this equation by 3. Those will just cancel. We get x plus 7 is equal to 21x plus 3. And then we'll want to subtract an x from both sides. Subtract a 3 from both sides. So 4 is equal to 20x. And then divide both sides by 20. And we come out with x is equal to 1/5. Okay. All right, now like I mentioned above though, with log equations we have to be careful. Log functions have domain restrictions. You can only take the log of a positive number. So when we check our answer, what we need to check for is that the argument of every log in the original equation is positive. Okay, so let's go ahead and check our answer. Okay, so I'm going to look back at the original equation up here, and I'm going to plug in what we found, the 1/5. Doesn't look like a 5. Maybe rewrite that. The 1/5. Okay. All right. So we would have the log of 1/5 plus 7 minus the log of 3 is equal to the log of 7 times 1/5 plus 1. Okay, so plugging that 1/5 in for all of our x's. Okay, now I'm just going to clean this up a little bit. So 1/5 plus 7 would give us a 7.2. Log of 3, there's nothing to do with that one. And then 7 times 1/5 plus 1 gives us a 2.4. Okay, now the only thing that I care about here is if the argument of all of the logs is positive. Okay, I'm not actually going to go through and check that this is equal. Okay, assuming all of our math was correct, then it will work as long as our number's within the domain. So 7.2 is a positive number. 3 is a positive number. 2.4 is a positive number. Since all three of these arguments are positive, 1.5 is a solution to this equation. If any one of these came out as a negative number inside the log, then you would cross it off and you would have no solution to your equation. Okay, so you have to do this check to make sure that you don't have any extraneous solutions. All right, let's go ahead and look at another one. Let's try the log of x minus 2 is equal to the log of 2 plus the log of x plus 3. All right, so once again, we're going to use our one-to-one property, but in order to do so, we have to first condense the right-hand side, okay? Remember, when you're thinking one-to-one, you have to have one log on each side. If you have two logs, that means you got to condense it first. So in this case, our two logs on the right are being added, which means we can condense it using the product rule. So that would become the log of 2 times the quantity x plus 3. All right, and we can go ahead and distribute that 2 in. So that would be the log of 2x plus 6 on the right-hand side. From here, we have one log on each side of our equation, so we can use the one-to-one property, get rid of the logs, and set the arguments equal. So x minus 2 is equal to 2x plus 6. From here, just solve for x. So we can go ahead and subtract an x from both sides, subtract a 6 from both sides, which should give us x is equal to -8. All right, we don't know if that's an answer yet, though. We have to first check what we just got. So check your answer. And we're going to plug this -8 back into the original equation. Always make sure you're going back to the original. All right, so we would get the log of -8 minus 2 is equal to the log of 2 plus the log of -8 plus 3. Simplify these. So that would give us the log of -10 is equal to the log of 2 plus the log of -5. All right, so remember, in order for this to be an answer, we can only have positive numbers inside of our logs. But if we look at these, my very first log here, I can see we have log of a -10. You can't do that. You can't take the log of a negative number. So it doesn't matter what's happening in any of the rest of them, okay, which you would also see the last term is an issue. You have a -5 in there. But as soon as you come across one log that has a negative number in it, it's out. So that means that -8 is not an answer, which leaves us with no solution. All right, so there's a couple more examples using this one-to-one property if you look at the notes on Blackboard, but I'm going to go ahead and show you how to use the definition of a log. Okay, so recall our definition of a log says that if b to the power of x is equal to y, then the log base b of y is equal to x. Now we used this definition in the previous video to solve exponential equations by switching from exponential form to log form. So in order to use this to solve log equations, we're going to switch from log form into exponential form. Now, the one-to-one property is used when every single term in your equation has a log in it. The definition of a log will be used if there's at least one term in the equation that does not have a log. So let's go ahead and take a look at some examples. And solve each equation. All right, so let's say we have the log base 4 of the quantity x plus 3 is equal to 2. All right, so in here, if we want to solve this equation, we can switch it into exponential form. Now again, like I said, the reason why we're using the definition on this one and not the one-to-one property is because we have this term, 2 in this case, that doesn't have a log attached to it. Whenever you have a term that doesn't have a log, you cannot use the one-to-one property because one-to-one property, you have to have the same log on both sides of the equation. So instead, we're going to switch this guy into exponential form. So our exponential form of this equation would be 4 squared is equal to x plus 3. All right, well, this is simple enough to solve. So I'm just going to rewrite my 4 squared as a 16, and then just subtract 3 from both sides, and we come out with x is equal to 13. Again, check your answer. So plug that back into the original equation. So we would get the log of 13 plus 3 is equal to 2, or the log of 16. Oh, log base 4. Sorry. Log base 4 of 16 is equal to 2. All right, double check that your arguments are all positive. So the only argument we have of a log on this one is the positive 16. That's a positive number, which means 13 is our solution. All right, let's take a look at one more. Say we have the log base 2 of x plus the log base 2 of x plus 7 is equal to 3. All right, so on this one, in order to use the definition of a log, we're going to have to first start by condensing the left-hand side. So you'll notice that these two terms are being added, so we can condense this using the product rule. So it would give us the log of x times the quantity x plus 7 is equal to 3. So we can go ahead and distribute that x in. So the log base 2 of x squared plus 7x is equal to 3. All right, so once you get everything condensed, now you can use your definition in order to switch it into exponential form. So exponential form of this one would be 2 cubed is equal to x squared plus 7x. All right, so this time we're looking at a quadratic equation. Remember, to solve a quadratic equation, you have to set it equal to 0. So let me first rewrite my 2 cubed as an 8, and then set my equation equal to 0. So subtract the 8 from both sides. From here, we can factor. So this would factor as x plus 8 and x minus 1, which would give us two solutions, x equals -8 and x equals +1. All right, we have to check our answers though. So this time we're going to have to do two checks to see if both of these work. All right, so let's start with the -8. So we'll have the log base 2 of -8 plus the log base 2 of -8 plus 7 is equal to 3, which would give us the log base 2 of -8 plus the log base 2 of -1 is equal to 3. Looking at our arguments though, I can see that both of these logs have negative arguments, which means those don't work, -8's out. So let's check the other one as well. So we'll have log base 2 of 1 plus the log base 2 of 1 plus 7 is equal to 3, or the log base 2 of 1 plus the log base 2 of 8 is equal to 3. In this case, 1 is positive, 8 is positive, which means 1 is our solution. All right, let's take a look at another one. Let's say we have, and I'm not going to do all of the examples from the notes, but just kind of picking and choosing some to go over. Let's do 3 times the natural log of 2x is equal to 12. All right, so on this one, we have to start by simplifying a little bit, and primarily that's going to come down to this 3. So because we just have this one term here, we have a choice with our 3. We could either bring it up as an exponent using the power rule, or we could divide both sides by 3, right? Because if we were to bring it up, that would give us a cubic function. It would be a little bit more complicated to solve. So the easier way to go here is just going to be divide both sides by 3. You would still get the same answer if you used your power rule to bring it up as an exponent as well. Your process would just look a little bit different. So if we divide by 3, we get the natural log of 2x is equal to 4. From here, we can switch it into exponential form. And remember that the base of a natural log is an e. So this would become e to the power of 4 is equal to 2x. Just divide by 2 on both sides, and we get x is equal to e to the power of 4 divided by 2. And if you want a decimal approximation for that, this would be, if we plug it into our calculator, approximately 27.299. All right, as always, check your answer. So plugging it back into the original equation, you have 3 times the natural log of 2 times 27.299 is equal to 12, or 3 times the natural log of 54.598 is equal to 12. So our only log here has an argument of a positive 54. So since that's positive, the 27.299 is our answer. All right, let's go ahead and do 1 or 2 more. Let's try this one. Let's do 1 minus 2 times the log base 6 of the quantity 3x minus 4 is equal to a -1. All right, so this time there's nothing to condense, but we want to start by isolating our log. So I'm going to subtract 1 from both sides. which will give me negative 2 times the log base 6 of the quantity 3x minus 4 is equal to negative 2. Divide by a negative 2 on both sides, which would give us the log base 6 of the quantity 3x minus 4 is equal to 1. Now that we've isolated our log, we can switch it into exponential form. So 6 to the power of 1 is equal to 3x minus 4, or just 6 is equal to 3x minus 4. And then solve for x. So add 4 to both sides, and then divide by 3, and we get x is equal to 10/3. As always, check your answer. So plug this back into the original equation. 1 minus 2 times the log base 6 of 3 times 10 over 3 minus 4 is equal to negative 1. So 1 minus 2 times the log base 6 of 6 is equal to 1. Check our argument. 6 is a positive number, so 10/3 is the correct answer. All right, guys, so there are a lot more examples if you look in the notes that I posted on Blackboard. So definitely go ahead and take a look at those. And if you have any questions on any of them, send me an email and I would be happy to make additional videos going through more examples if you need to see it. All right, so make sure you do the lab on this section. And then also after the lab, there is a little mini review in the middle of the unit that you guys can go through for some extra practice with this as well.